ds, how am I going to prove that this is going to be equal to 1? Okay, I told you. Now, when I take a look at this, I can let z be x minus mu over sigma. Okay, and if that happens, the z dx, the z dx here is going to be 1 over sigma, and that's going to imply the s equal to sigma dz. Okay, now when I come back here, negative infinity to that, 1 over, this is sigma over root 2 pi, and this is z squared instead of ds, I have a sigma dz. Okay, so these cancel that. Oh my God, take a look at that. Do you know if I have negative infinity to this, okay, what I have inside here, that's a standard normal distribution. Okay, in statistics, if x follow normal with parameter mu sigma, then z follow normal with parameter mu1, mu01, which means the mean of this is 0, the mean of the variance is 1, and this guy here, f of z, is 1 over square root of 2 pi this. This is what we call standard normal distribution. Okay, why do we need a standard normal distribution? Okay, because if I want to find probability using normal density, is to be complicated. And because one of the properties of a normal distribution is that it depends on the mean and standard deviation. Okay, for instance, we are comparing the several means. Okay, we could have several means, we could have several standard deviation. That would be complicated. Can we have a way to have a uniform value to restrict the values of the mean and the variance to a particular value? That is when we use the standard normal distribution. Let me tell you this. Normality facilitates standardization. I'm going to say that again. Normality facilitates standardization. Standardization facilitates the use of z-score, the use of z-table. You know, if I want to calculate probability with normal distribution, I don't need to be worried. I don't need to worry about calculus. All what I'm just going to do, I'm going to use the idea of this. I'm just going to go to the table. So on Friday, I'm going to show you how to read a z-score value from a table. Does that make sense? So, like I said, this is another probability distribution. We call it standard normal distribution. And if you take a look at this guy here, the standard normal distribution will integrate. This is actually going to integrate to 1. Okay, this is going to integrate to 1. Now, that is for that. The number 4, we're still on the property. Okay, so another property here is that all normal curve, or let me just say normal density normal curve depends on the values, depend on the values of mean and standard deviation. Okay, for example, take a look at this guy. Do you see that here? You have 3 curves, right? And they have the same center. Can you see all of them have the same center? They have the same mean, but they got different standard deviation. You can see that. And this is another one where they got different center. Different center mean they have mean 10, 15, 20, but they have the same standard deviation. So which means normal curve, the shape of a normal curve depends on the values of the mean and the standard deviation. So that is going to be property number 4. Does that make sense? Is there any question about that? Okay. Now, the next thing another property that I want to talk about, okay, number 5, when I want to talk about the limit, when x tends to positive limit of f of s, okay, the normal distribution f of s will be equal to 0. even when s tends to negative limits, f of s also going to be equal to 0. You can investigate that. Okay, so that is this is another property. Okay, when s tends to infinity or when s tends to negative infinity, f of s is going to be equal to 0. Okay, then another thing I want to talk about, number 6. Okay, I want to talk about that all normal curves, they actually are going to be, they're going to have a bear shape with a point of inflection. So all normal curves, okay, have bear shape with point of inflection, okay, with point of inflection at mu plus or minus sigma. Okay, you can actually derive this. Okay, what do we mean by point of inflection? I want to talk about point of inflection. You know, the point of inflection is actually, you want to talk about the rate of change of a slope. That's a second derivative. Okay, situation where the slope, that very curve change a sign, maybe from increasing to decreasing. Okay, now if you really want to prove this, I'm trying to say this occur when s equal to this. You can prove this from a normal distribution. I'm going to give you a clue because of my time. Okay, I'm going to give you a clue on how to do that. Okay, when you have a normal distribution, okay, so when you have a normal distribution, if you do the first derivative of a normal distribution, you do the second derivative of a normal distribution, then you set it to 0. When you set it to 0 and solve for x, then I'm trying to say your s is going to be this. Try that. Okay, you want to figure out how the point of inflection. The point of inflection has a statistical implication. Okay, when you take a look at this is actually trying to say one standard deviation within the mean. Okay, one standard deviation within the mean. Mu minus sigma is going to indicate one standard deviation below the mean, and mu plus sigma is going to be one standard deviation above the mean. So this is a point of inflection, and in statistics, the implication is that it enables us to understand the variation in the distribution as well as the shape in the distribution. In statistics, we value the shape, okay, for us to be able to know the kind of intervention. So if you try all this for that, you actually, you're going to have that. Now, the last thing I'm going to talk about, normal distribution, before I go into what I'm going to derive the moment generating function for normal distribution for you. But let's talk about the height of any normal curve. The height. Okay, when I say the height, I'm talking about this guy, which is the mean, right? Okay, which is the mean. The height of any normal curve is the mean. Okay, so now if you want to do the height of any normal curve, okay, so number 7, the height, okay, of any normal curve, okay, the height of any normal curve is the mean, okay, which is, x equal to mean. Well, how am I going to do that? I first need to take a natural log of the f of s, okay? After taking the natural log of the f of s, of course, it's like I have a log of exponential. Maybe I should be using this. Ln and log of exponential mean the same. So ln of 1 over square root of 2 pi sigma squared, this s minus mu sigma all squared. So when you take the ln of that, so you're gonna have ln. If you take a look at this guy, 2 pi sigma squared raised to power that minus half x minus mu over sigma squared. okay, which is minus half ln 2 pi sigma squared. This x minus mu over sigma squared. This is the natural log of the normal distribution. What are you going to do? I'm going to differentiate that. I set to 0. Okay, I want to differentiate the ln f of x dx. Okay, if you differentiate this and you set to 0, okay, and solve for x, okay, you're actually going to have s equal to mu. Okay, and if you really want to see whether this is a local maximum, okay, if you want to see whether it's a local maximum, then you differentiate again. When you differentiate again, your expression should be negative. When the second derivative is less than 0, that's a maximum, right? Okay, now when you differentiate, when you do the second derivative, so when you do the second derivative, I think that is going to give you this, if you can try that for normal distribution. And this is less than 0 because sigma squared is positive, but this is going to be negative. So which means that guy is, is a local maximum. Okay? That guy is going to be a local maximum. Now, the last thing I'm going to do before I go